Hello, good morning, everybody. This is from United Kingdom, wherever you are. Good morning, evening, afternoon. All right. So we have done two lectures so far, and this is gonna be the last lecture for this topic. We have done electromagnetism, all right, the induction, how it is induced. We have learned Lenz's law. We have learned the actual Faraday's law of electromagnetic induction, where flux are involved, all right, where the flux surface and the loop that is surrounding that surface is connected, interconnected. Okay, so we have learned the basic concept so far. We have learned in detail everything so far. Now something is remaining, and today I'm not gonna say timer because it's a small topic, but it's very very important. Okay, I'll show you something very intuitive today. Very very intuitive. All right, I will show you something which is very intuitive, and you should be very, you know, you will only see this in once in a lifetime. Okay, let's begin. Mm, just a minute. I'll just hold this board up. Okay. So here, what you need to understand is I make a circuit. Here is a resistance. Ah, here is a resistance. And here is battery. Let's say for simplicity, the EMF in the battery is 1 volt, and this is 100 volts, 100 ohms. Okay, 100 ohms, and this is 900 ohms. All right. Now, if I ask you, what is the value of a current in the circuit? It's a very easy question, right? What is the value of a current in the circuit? So easy question. I mean, we are studying such a great topic, and you might feel I'm giving the school topic. No, just be with it. So you'll say that total resistance V equals IR. So V by R, total resistance is gonna be 1,000. All right. So that's our current. Our current is gonna be our current is gonna be 10 to the power minus 3 amperes. So this is the current we have. This is the current we have, isn't it? Yes or no? Yes. I'll show you something very interesting. Please be with it. This is very, very important. Though it might seem such a simple topic, this is very important. All right. Now, if I ask you, what is the voltage drop? What is the potential difference over this resistor? Or if I point this point as a VD, and if I point this point as a VA, all right, and VA, okay. Now, please see here very carefully. What is VD? What is VD minus VA? Or basically, what I'm saying is, what is the voltage drop at 900 ohm resistor? What is it? You will simply do it. If I do simply, what I'll find is I times r. Okay, I is 10 to the power minus 3 times r 900. So 900 divided by 1000, you'll get 9 by 10. Okay, 9 by 10. And what you'll find is you'll find this as a zero point 0.9 volts. 0.9 volts. Okay, and just for our simplicity, because here is positive, just for our simplicity, okay, this is positive, all right. Mm. uh, Current is going in this direction, all right, isn't it? Current is going in this direction, isn't it? Current is actually going in this direction, isn't it? Just for our simplicity, I take the current direction in this direction, all right, because I just want to make it positive. I don't want to make it negative. That's it. That's my point. We are using Kirchhoff's, Kirchhoff's, right? This is loop, Kirchhoff loop 1. Okay, so we are using Kirchhoff's rule. So IR, okay, I did IR, isn't it? Now here, what you will see is I am moving from, current is coming this direction. I am moving from current always moves from higher potential to lower potential, not lower potential to higher potential. Okay, so I'm moving from lower potential to higher potential, isn't it? That is why I took it plus zero point 0.9 volts. Just for simplicity, I can show you by minus. I just don't want it. All right. So in the similar manner, if I ask you now, what is the potential difference? What is the potential difference on the next side, on this side of the circuit? That means what is the potential difference? What is the potential? I just did this, man. This should be 100. Okay. 100 is so weird. We didn't do it in 100. Okay. I didn't know it. Okay, this one is okay. All right. What is the voltage drop on this side? This side. All right. So what I'm basically asking is I'm asking VD minus VA. VD minus VA. Okay. Come on. VD minus VA. Now VD minus VA we know is open 9 volts, isn't it? But we moved this direction, okay, VD minus VA, okay, in order to calculate VD minus VA. VD minus VA, we moved this direction. Now we will move this direction, VD minus VA. VD minus VA. What I am trying to do is this zero point 0.9 volts, okay. VD minus VA means voltage drop between these two in this side. Okay. Now, if I've used Kirchhoff's loop in the opposite direction, for example, in this direction, and then it would have been minus zero point 0.9. But what I'm trying to do is, here is a voltmeter. So I am trying to show you like so I'm trying to show you is if I check the value voltage drop in 900 ohm resistor, it will show zero point 0.9 volt IR, isn't it? I'm trying to show this. Now forget the loop. Let's because it might create confusion on the direction. I'm just trying to okay I'm just trying to make you understand. We are just calculating voltage. Okay, voltage. Now Kirchhoff, even if I use Kirchhoff's rule, Kirchhoff rule, I'll get zero point 0.9 volt. Okay, like for simplicity, let me just take this. Let me just erase this. Come on. Let me just erase this and let me make the circuit go in this manner. Okay, if you want that, I can do that. Then we will have here minus 0.9 volt. Okay, that's very fine. That's very perfectly fine, isn't it? Now, now what I'm gonna do is I want now if we have to calculate VD minus VA, VD from VD to VA we will go to minus 0.9 volt. Now if you just go VD minus VA in this direction, now in this direction, okay, VD minus VA, okay, VD minus VA, then what you will find? What you'll find? You will simply find that current in this is in this direction, isn't it? Current is in this direction, isn't it? We are going from higher potential to we are going from lower potential to higher potential. Then what you'll find is 100 ohms, 100 ohms IR, R times 10 to the power minus 3, that will simply be zero point 0.1, zero point 0.1 volts, okay, plus zero point 0.1 volt, because we are going from higher potential to lower potential, VD minus VA, okay, and minus, we will be moving from positive to negative, so it will be minus 1 volt, which will again give me that it's minus 0.9 volts. All right, so this is Kirchhoff's law. In first, we moved in this direction. In second, we moved in this direction. We are calculating VD minus VA. There is no any difference in calculation. We are just calculating VD minus VA. Okay. So if you see VD minus VA, we are getting minus zero point 0.9 volt. Let me change this. We are getting minus zero point 0.9 volt. Okay. And we are again getting minus zero point 0.9 volt. Okay. If I attach a voltmeter right here, if I attach, then what happens is here I will get zero point 0.9 volt. We are ignoring minus because that's a that's a different case, okay? Because in voltmeter we will get zero point 0.9 volts. That's how it is. And if I put a voltmeter, now you will see something different, okay? If I put a voltmeter right here, if I put a voltmeter right here, it will also give it will also give zero point 0.9 volts. Zero point 0.9 volts. Okay. So here you see zero point 0.9 volts, here you see zero point 0.9 volts. Now you might ask, sir, what is this? We know that voltage in parallel is same, isn't it? You know it. Yes or no? You know it, voltage in parallel is same. Now here is the thing. What is the thing is, now here is the thing. If you understand here, okay, now here is the thing. Everything is hidden here. All right. If you understand it, you will get it. If you don't, you will not. It's a very easy topic. You will understand conservative and non-conservative field also. Okay. You will understand conservative and non-conservative field also. You'll understand everything. All right. Let me use pain. Let me make it 900. Okay, let me complete the circuit. Now, what I wanted to do was not that. I wanted to remove the battery. Now there is no EMF. Now there is no EMF. And now a current is induced in this circuit by electromagnetic induction. Magnetic field is here. So to have a current in this direction, What should be the magnetic field to have a current go anti-clockwise? To have a current go clockwise, this anti-clockwise. So this, okay, current must be in. So using the right hand rule, you'll find it. To go clockwise, you'll have magnetic field. Magnetic field will point anti-clockwise, make current anti-clockwise, but current induced will be such that it will go clockwise. So a magnetic field will be pointing towards me. Okay, so pointing towards me, so magnetic field is out of this laptop. All right, out of this. So magnetic field is towards me, towards you guys. Lenz's law. Okay, now a current is induced, and let's say, for example, for our convenience, for for now, that induced current, that EMF induced, let's say EMF induced is now 1 volt. At an instant in time, the EMF induced in this circuit is 1 volt. You must see there is no battery in this circuit. There is no battery in this circuit. EMF induced is 1 volt. Please see this. This is very important. EMF induced is 1 volt. There is no battery in this circuit. Okay. Now there is no battery in the circuit. Now this is VD. We have VD. Okay. Now if I ask you, what I ask you is, if I ask you, uh, VD minus VN. Now if I ask you the potential drop at 900 ohm resistor, then what you'll say? What is your answer? Now if I ask you, the potential drop in 900 ohm resistor, then what you'll say? What is your answer? Please say me. Come on. Okay, said. Now I'll say just a minute. Okay. Now I just asked you what is VD minus VA. I just asked you. Okay. So what is VD minus VA? If I move in this direction, now Kirchhoff's law won't even bother. Okay, Kirchhoff's law. Even if we'll, okay, let's use Kirchhoff's law. Previously we had minus zero point 0.9 volts. Okay, using Kirchhoff's law, and here also we have minus zero point 0.9 volt using Kirchhoff's law, because we know that in parallel voltage is same. Okay, but in voltmeter we will have zero point 0.9 volt, zero point 0.9 volt. Okay, it's just a question of direction, Kirchhoff's direction. All right. Now if I ask you VD minus VA, VD minus VA is still because the current, because the voltage is 1 volt, EMF is 1 volt, current is still the same. So IR, so voltage is still 0 minus 0.9, minus 0.9. Please see this. This if I go clockwise. This if I go clockwise. Now let's go anti-clockwise. Now let's go anti-clockwise. What you'll see is current is 10 to the power minus 3. You will see that VD minus VA is, we have, this is higher potential, this is lower potential, to higher potential we will get O point, will get zero point 0.1 volts. We will get zero point 0.1 volts. If we go anti-clockwise, okay, for now, I'll just remove minus just for simplicity. Don't get in minus. This is just a question of Kirchhoff's plus minus. It's the same thing. All right. So you will get zero point 0.9 volts here, which is the same. Voltmeter will show zero point 0.9 volts, but here previously it was showing zero point 0.9 volt. It will now show zero point 0.1 volt. This is amazing result. This is so amazing result that it has made some professor look at it, some physicists look at it. I'll give you the reference of this topic in a while. So we will get zero point 0.1 volts. Now say me, we are calculating the same potential difference. So in parallel, the potential difference are not same. How is that possible? Potential difference are not same. How is that even possible? Hmm? How is that even possible? Potential difference are not same. Hmm? How is that possible? Potential difference are not same. This is what happens in, okay, just let me show you one more thing. Okay, using Kirchhoff's law, you will find, suppose if I do Va minus Vd, Va minus Vd, no. What I was gonna do is Vd minus Va, Vd minus Va, okay, Vd minus Va minus Vd minus Va minus Vd, Va minus Vd, okay. So Vd minus Vd, Va minus Vd. No. Something must be there. 0.1 volts. Va minus Vd, Va minus Vd. Okay. So something like this. Just a minute. Uh, it's not like this. Va minus Vd. So if Va minus Vd, so Vd minus Va is 1 volt, okay, minus Vd minus Va is 0.1 volt, and Va minus Vd is, just a minute, Va minus Vd, what happened? Minus 0.1, 0.9 volt, it will be, uh, it will be 1 volt. Open, okay, I get it. It will be Va minus Va, it will be, because it is minus zero point 0.9 volt, it will be now be 0.9 volt. Okay, now if you add this, you will find there will be 1 volt, and this is going to be cancelled. This is a great result. Please see this. This is a great result. What this is saying is the EMF 1 volt that we had in the circuit previously, the EMF 1 volt that we had in the circuit previously is there, but in the form of induced EMF, not in the form of battery. There is no battery, and in the potential difference, parallel potential difference is not same. Now the question of potential difference changes. Potential difference is not the same thing what we have thought. Okay, potential difference is not the same thing what you have thought now. Now the very question changes. So this is what happens in non-conservative field. In non-conservative field, Kirchhoff's law doesn't works. Kirchhoff's law doesn't works. Okay, in non-conservative field, Kirchhoff's law doesn't work. The only law that holds is Faraday law of electromagnetic induction, that is DDT, of uh, open surface integral, b dot da, okay, b dot da, we have minus sign here, equals to closed loop integral of E dot dl. This holds for everything. Faraday is the main guy. Michael Faraday is the main guy, not Kirchhoff's. Kirchhoff's is just for conservative field. For a non-conservative, for any field, this will work. Okay, so we've come to a different understanding now. Potential difference, you will find the understanding of potential difference is changing, everything is changing. The main formula is this, not Kirchhoff's. And in non-conservative field, potential difference is path dependent. What I'm trying to say is, in previously, no matter if you go this path or if you go this path, the potential difference is same, but not in conservative field, not in non-conservative field. In non-conservative field, it is different. Minus 0.9 volt, 0.1 volt. You see it clearly different. So what I was trying to make you understand is, I was trying to make you understand conservative and non-conservative fields. Okay, and what Kirchhoff's told was that E dot dl is always zero. Kirchhoff told E dot dl. That means if you go around a circuit, you will end up zero. But what you have found is, if you go around a circuit, we have 1 volt extra. So it doesn't hold. Please see very carefully. It doesn't hold. So Michael Faraday is the main guy. It is not the Kirchhoffs. So this is how conservative and non-conservative field you will understand. So this was one of the topic. Why I choose this is one of the topic that Professor Walter Lewin from MIT discussed, and this when Professor this did this experiment, no any other professor believed it. Okay, so I'll give you a paper reference where you will find a detailed explanation, detailed derivation of this process. I'll provide you in a while. Okay, I'll put it in my bio or something. I'll do it in a while. So that's now for today. We are done with electromagnetism and everything. This was very important topic which you needed to be understand. Okay, so that's it. Now I'm leaving you guys. Next, now we will be starting next topic, that is electric field, especially Gauss law. Okay, we will be starting next. Maybe I'll start tomorrow, or I don't know. So till now, if you have any confusions, please do approach me. If you have any confusions, do know me in the comments. And that's it for today. Take care. Bye bye.